Welcome to Under the Microscope. This series is brought to you by the Real Scientists Nano team. Our goal is to provide a platform where scientists can communicate their work and interact with the public. With that in mind, every week we introduce you to a scientist working in the field of materials and nanoscience, who would be curating the RealSci_Nano Twitter account.
Hi everyone, today we have with us Andress Castellanos Gomez, who is a tenured scientist at the Spanish National Research Council in Madrid, in Spain. Hi Andress, how are you?
Hello, fine, thank you.
Super. Let's start by understanding your research journey a little bit. So how did you end up in your current research field?
Yeah, so I basically started from my PhD already working on two-dimensional materials. So when I started my PhD, the exfoliation of graphene was kind of like a brand new topic. So back in 2006, there were not so many, groups working on that experimentally. Right. So I was advised to start working on two-dimensional materials, not only graphene but other materials. And basically, since then, I've been working all the time in two-dimensional materials. All along the years, I've been changing the techniques and the scientific questions I'm focused on, but always on two-dimensional materials. For example, in my PhD thesis, I was working mainly on scanning probe microscopy techniques in order to test, to probe the local properties of two-dimensional materials. And right now we are mostly focused on of optoelectronic devices with two-dimensional materials. So basically we have changed a little bit the topic, but always centered around two-dimensional materials.
Okay. You mentioned that right now you're doing more the fabrication of these electronic devices. So how big are these devices? Just like approximately, what dimension are we looking into here?
Yeah, well, they're microscopic devices. So our typical devices, they have, let's say, a thickness of 1 nanometer. So because they are made with two-dimensional material, they are atomically thin. And our channels, they are typically on the order of 10 microns. So they're also not like the smallest transistors or photodetectors ever, but also they are not big, right? So they are kind of like research dimensions, let's say, something in the micron range.
Absolutely. I mean, 10 micrometer, that's really, I would say that's still quite small. It's definitely small, for sure. For sure, yeah, absolutely. So you basically started your PhD work in the 2D materials, and I think 2006 was the Nobel Prize wasn't awarded yet, right? That was in 2010.
It was in 2010. That's right. So exactly when I was finishing my PhD. So I finished my PhD in March 2011. And I think the Nobel Prize was awarded at the end of the year, of 2010, because I was in that time in Groningen. I remember I was doing a short stay in Groningen in the Netherlands, and the Nobel Prize when awarded to Novo Silicon Gaim there. Yeah.
Okay, just a fun question here. Were you exfoliating graphene when the Nobel Prize was announced, or in that week or on that day? Were you exfoliating graphene in your own lab for your work in Groningen?
At that time, I was mostly working on other two-dimensional materials. At that time, I was already working a lot on dichalcogenides, insulators like mica. Yeah. So not that much graphene at that time. I mean, since then, I think since 2008 or something like that, I focused mostly on semiconducting two-dimensional material. Yeah.
Okay. All right. Super. And now, where, like your current research, I mean, you spoke about your scientific journey, of course. So where do you see your current research fitting in this big picture of materials or nanoscience? I mean, you already spoke a little bit about it in the short podcast, but maybe in a broader sense, like in this big field of materials or nanoscience, where does your research fit?
Yeah, so our our research in my group is basically exploratory in a sense, right? So that we work a lot on doing like the first kind of study of novel materials, isolating new two-dimensional materials. So basically, we are at the, let's say, the forefront of two-dimensional materials research in that respect. So we are every day bringing new two-dimensional materials for the community to keep playing. And regarding the scientific questions we work with, so we are into the optoelectronics field. We are more and more working in an emerging field that is called straintronics, that is based on changing the properties of a device by applying a mechanical deformation. Okay, and if I have to put this into a broader picture, I will say that we are trying to develop new concepts of electronics. Okay, so beyond, let's say, the traditional scaling down of the electronics, you know, the semiconductor industry keeps scaling down the transistors more and more, and of course there is a fundamental limit for the scaling down that it cannot be overcome, the tunneling of electrons, and then once you reach a certain level of semiconductor dimension, then you start having tunneling and you cannot scale down more your transistors.
Right.
And one of the approaches to overcome this problem is to fabricate devices with more functionalities. Okay, not just a transistor, but a transistor with something else. Okay, this is what is called in the, let's say, the jargon is called more than more. Okay, so it's not only making smaller transistors, but making transistors that they can do other things. And then in this kind of is more than more, you have the spintronics, you have the photonics, all the onyx, okay, are into this kind of field, and therefore our straintronics is also in this field. So we want to fabricate devices in where you can, of course, have a tuning knob with electric bias and so on as a normal transistor, but also you could use a mechanical deformation as a tuning knob to change the output characteristics, and that is what, let's say, the broader picture of what we do. I mean, we isolate new materials and so on because it's part of our business, but our long-term project is to try to develop these new kind of electronics to, in the future, try to overcome the problems with the electronics miniaturization.
Okay, that is so cool. I wasn't aware of this. That of course, like the transistors are going like smaller and smaller, but it's such a simple thought, but it never occurred to me. And I just realized after you said it that of course you can scale it down, but you can also add more and more ways that it can function. So not just the on and off, but other things as well. That is so cool. That is so amazing, and I hope it works. I hope whatever you're doing in the lab comes into my phone in 10 years or 5 years down the line.
Well, even if our approach doesn't work, I'm pretty sure that somebody else's would, and that is the part of the story, right? So that what we have to do is we have to invest in our direction. Okay, so we are confident that this is a good direction to go and so on, but you never know, of course.
Right.
But I think like if all the research groups they do an honest work in different directions, they will complement each other, and eventually one of them will be actually useful. And I mean, even if ours that is let's say not used in the cell phones in 10 years from now, if our contributions makes that some other special electronics make it into the phone, then we will be happy with it. Yeah.
That's very noble of you. You spoke like a true scientist who cares about the science and not your science. That is really nice of you.
Well, it's true that once you are so how to say it honestly? I'm going to say it honestly. Yeah.
You
So
can.
once you are tenured, I think you should start thinking more, novelty about novelty about the science and not about your career anymore.
Right.
It is true that a lot of big old professors, they keep telling you, no, you shouldn't care about publications, you shouldn't care about citations. And that is very simple to say once you are tenured. Okay, so
Yeah.
I know that once you're a PhD student or you have to take care of your own career, that's for sure. But I think once you're, let's say, once you have your position and you're safe, let's say, I think you can make a little effort on thinking less on your own, let's say, career and thinking more about like the community. Huh?
Right, right. Yeah, that makes sense. That makes complete sense. So it going to the science, and I think your science is so cool. So it sounds like you've been involved with a lot of research projects and a lot of interesting experiments, not just right now, but also so far in your career. So this question is difficult, I know, but if you have to pick one project that you're most proud of, or the most fun or quirky one, could you pick one project and explain it to us in simple words in the section we call In Other Words?
Yeah. So right now we have an ongoing project that is funded by the European Research Council.
Mm-hmm.
That is it's a very prestigious project, and I'm pretty proud of it because basically it gathers all the background that I acquired during my career into one project.
Mm-hmm.
So I've worked a lot on the materials, let's say basic characterization, isolation, and so on. I worked a lot on nanomechanics, and also in the last years a lot on optoelectronics.
Mm-hmm.
And this very last project is involved about um, mixing all these things together in order to develop this field of straintronics I was talking previously about. So the idea is to fabricate optoelectronic devices with two-dimensional materials
Mm-hmm.
in where we can apply a mechanical deformation in
Mm-hmm.
order to tune the output characteristics of the. For example, a photodetector, okay, where if you apply a mechanical deformation, if you stretch it, for instance, you can increase the spectral bandwidth. So let's say a photodetector that detects in the visible range, and if
Mm-hmm.
you stretch it a little bit, then it starts detecting in the near infrared, mid infrared, far infrared. Right? So the idea is to make a photodetector that is tunable, and you can tune it with a strain, no? With a mechanical deformation that you apply externally at will.
Mm-hmm.
Uh, that is basically the final outcome, the final goal, let's say, of the project we're working on right now.
Mm-hmm. Mm-hmm. Okay. Wow, that's so just by stretching it, you are changing the property, like the detection property of this particular material. Can you tell us which this material is, or would you
Mm.
rather like, okay, read it when I publish it?
No, it's okay. It's okay. So basically, we are working on applying this kind of approach for any two-dimensional semiconducting material. Okay,
Okay.
we're starting working on molybdenum disulfide, and recently we started also applying it to indium selenide. But I mean, it should be a general platform that could be used for any two-dimensional semiconducting material. So the physical principle is rather general, because basically what you do is when you apply a mechanical deformation, you're separating the distance between, I mean, if you stretch, you separate the distance between the atoms, you increase the bond length. If you
Right.
compress, you just reduce the bond length. And
Right.
basically the potential landscape that the electrons feel changes with this change in the lattice. And
Right.
therefore it changes the band gap of the semiconducting material.
Right.
Then if you change the band gap, you change the spectral range that the photodetector can detect. So
Right.
it's rather general. The only trick here is that two-dimensional materials are really suited for straintronics because they are really very resilient to mechanical deformations. They can be stretched by a humongous amount of strain without breaking.
Mm-hmm.
That makes them quite suitable for strain engineering. Yeah.
Right, right. So, okay, this might sound like a stupid question, but I'm gonna ask it anyways. Did it ever happen that when you're stretching this material, that it just kind of like broke, and you were like, okay, now we have to go lower with the stretching, and like, did that happen? And did you see that? Like, did you catch that happen? Like, okay, we went too far. Okay, next time we only go till here and not till like wider. Did that happen?
Yeah, that happens. That happens indeed. So the main failure mechanism is typically slippage. So that you apply strain, and basically the flakes they slip on the substrate, on top of the substrate, and then you cannot apply strain anymore. That is the main failure mechanism. But sometimes you can even see cracks. appearing on the flakes, and I mean literally breaking down the device by straining them. Yeah, sometimes you
Right.
can see it.
Right, right. Wow, this is so cool. I mean, I knew about it, but after you explained it, I just remembered how cool all this is. Just by stretching, oh my God, this is so amazing. This is so cool. And I can understand why you're doing it because it's so fascinating just to hear about it. And doing those experiments must be, and yeah, yeah, absolutely. And I can understand why you took picked this as the project the most proud of or the most fun one. Let's go with that. One of the most proud of. Let's go a bit towards your research experience, and I hope your research experience has been wonderful so far and will continue to be wonderful in the future as well. However, if you had three wishes to improve your research experience, what would you ask for? And I'm not promising anything here, okay?
Okay, I have this very, very clear. Less bureaucracy, less bureaucracy, less bureaucracy. Yeah, yeah, yeah. I mean, this is completely clear. I think, yeah, it's the only thing I hate of this business. So that it's getting more and more and more bureaucracy every day.
Okay.
You know?
Okay. Aren't you
Yeah.
getting used to it though with the bureaucracy? Aren't you used to do it by now?
No,
No?
not really. No, I'm not getting used to it.
No?
No, no,
Okay.
I'm still suffering.
I guess you also don't want to get used to it because you want to focus on the science and not the bureaucracy.
Yeah, yeah, yeah.
Oh, okay, okay, I understand. Well, I wish I could just do this and be like, okay, from tomorrow onwards, Andres, when you wake up next week, no
Mm,
bureaucracy, everything will just go as you want. No,
mm,
as less amount of bureaucracy. Let's not go with no bureaucracy, but less bureaucracy. I
mm.
wish I could say that. But do you think we are by we I mean the scientific community, the research council is trying to reduce it, or do they think that oh no everything is fine, this is enough, this is okay, we need it?
I don't know. I mean, there is of course a need for accountability. I mean, coming from society, that is clear. I mean, we scientists we are using mostly uh, taxes from taxpayers, and we need a certain accountability. That's clear.
Right.
Um, the question is if that accountability has to come all the time with such an amount of bureaucracy, or we could do it in a more transparent way, let's say. Yeah, I mean, I guess it's a complicated problem because I've been, like attending to talks of politicians and science policymakers and so on, that they keep promising that they're going to improve the situation, but the situation gets worse and worse. But I know that they are aware of the situation, but it keeps getting worse and worse. Yeah.
Oh, oh, I hope it gets better. I really hope it gets better. And in the near future or late future or foreseeable future, let's go with that. And speaking of future, what are you most looking forward to in the next 3 months?
Um, let's see. I mean, we are now trying to finish a proposal, okay, for a project that we are writing now. That it will be basically changing completely the gears in our lab. So it will be doing completely different kind of things. And I'm really looking forward to see the evaluation of this proposal, to see how because sometimes you think your idea is good, you get into it, you get excited, but until you don't get some feedback from other scientists, peers of you don't know if your idea is actually good or not. So I'm looking forward to see what this community thinks about this kind of proposal.
Okay. Okay. So there would be once it goes through and once it's approved, your direction will be different. Will it still be on the lines of optoelectronics or the nanomechanics, or will it change like drastically? Can you give us some hints here?
Yeah, yeah, I can give you a flavor of the project. So basically, now we work on, let's say, devices that they are just for research. Okay, so we fabricate devices with very high quality materials, but our devices they're small, they are homemade. All the devices are slightly different because we based of our devices on mechanically exfoliated flakes. Okay, and that makes the reproducibility smaller. But these devices are intended for, let's say, fundamental studies. Okay. The idea is that in the new project, we're going to start fabricating large-scale devices on paper substrates in order to fabricate ultra low-cost components based on two-dimensional materials. And let's say the idea will be the same, fabricating also photodetectors, fabricating solar cells, also some kind of like strain sensors and stuff like that. I mean, like similar kind of devices, but completely different, approach. I mean, we will be more focused on things like cost and reproducibility than things like performance. Okay, so we will be more focused on other aspects. Yeah.
Okay, sounds good. Whatever you told me definitely sounds good. And if I was in the approval committee, I would just vote for yes, yes. This one, yes, absolutely green light for sure. So I'll keep my fingers crossed that I can do.
Thank you.
But yeah, Andres, this has been wonderful speaking with you. And before I let you go, I have one last question for you,
Okay.
which is what do you think are the challenges faced by the scientific community, so the materials and nanoscience, or from your point of view, for your field, what are the big questions that you all are trying to answer?
Well, there are certainly like many challenges, no? So like if we focus just on two-dimensional materials subfield, I will say most likely the integration of two-dimensional materials with existing technologies. So most likely that is the main challenge right now. So like people can grow now large area graphene, large area molybdenum disulfide, etc., etc. But I still interfacing this material with CMOS technology it is quite difficult. I mean I'm not an expert on the field, but I've heard that it's quite difficult. If we think about, for instance, material science in general, I think maybe the most urgent challenge is the reproducibility. So I think we are facing a crisis of reproducibility. So we published a lot of papers. I mean, we have more and more and more scientists working in different labs and so on. And there are more journals, more papers published, all these things. And it's very difficult to reproduce the results of other labs. It's getting more and more difficult.
Okay.
I mean, I'm not talking here about like mispractice or anything, but I think we have to really work on this topic here because I think we are not maybe as thorough as possible on providing the details of the protocols we use, or I mean, it's a problem that we have to face as scientists, especially material science, basically.
Okay. Yeah, that makes sense. Yeah, the integration of the 2D materials into the existing technology, as you said, that's actually a very good point, and it's definitely a big challenge for sure. And also the reproducibility. Absolutely. I think we need, for the field of material science, we need some sort of guidelines or protocols like, okay, no, you have to make sure that just mention how many times this experiment worked, or how many times did this experiment not work, or something like that, so that it is possible to reproduce your findings in a different lab on a different continent. Yeah, that's definitely very
Yeah, I think like the kind of experiments we do, they are not standard at all, right? And therefore it's difficult to provide like the protocols with details, with enough amount of details, let's say. I know that in other fields of science, like I don't know, like some kind of like biotech stuff like that, they are super strict with the protocols, right? So, and then they have to be done in this kind of machine, in this. So I think that constrains a lot of science because
True.
you are not flexible, to improve or to explore all the things, but it will improve the reproducibility. So we have to try to find a trade-off between the two things. I think it's a very complicated problem. I mean, I have no clue how to solve it, but I think it has to be at least spoken at some point.
Right. Yeah, I mean, the first step is to identify the problem, and then the community can come together and try to brainstorm and find a solution. in solving it. Absolutely. So thank you very much, Andres. This was really nice, and looking forward to having you on Real Scientist Nano.
Thank you. Thank you so much.
Thank you for listening. To know more about us, please visit our website realscientistsnano.org and follow us on Twitter at realsci_nano.